Before watching this video, you need to have gone through the previous video where we looked at the rules for drawing Lewis structures in detail, including the example of drawing the structure for water. My next example is carbon tetrafluoride, CF4. The first thing I need to do is calculate the number of electrons in the structure. So my atoms are carbon and fluorine. And in this structure, my carbon is going to bring 4 valence electrons based on its position on the periodic table. In this structure, I have 4 fluorines that will each bring 7 valence electrons. So I have 4 fluorines that each bring 7 valence electrons. That gives me a total of 32 electrons for this structure. That is the total number of valence electrons that I have to assemble this Lewis structure. My Lewis structure must account for all 32 of those electrons. As I go through the rules, rule number 2 tells me to identify my central atom. Between carbon and fluorine, this is also an easy choice for the central atom because what I know is that fluorine is the most electronegative element on the periodic table, and the same way that hydrogen from our previous example will never be a central atom, fluorine will also never be a central atom. So that means that I'm going to put the carbon in the middle and bond the 4 fluorines to it. In doing so, I used 2, 4, 6, 8 electrons. So as I subtract those 8 electrons from my total of 32, that means that I have a total of 24 electrons left to complete the structure. Rule number 3 tells me to complete the octets for my outer atoms. In this case, my outer atom is a fluorine, and we know that fluorine is trying to bond to get to an octet. It sees 2 electrons already in this single bond, so in order to complete its octet, I'm going to give this fluorine 6 more electrons. And as I give the fluorine 6 more electrons, I'm going to give it those electrons in the form of 3 lone pairs. This fluorine will also see 3 lone pairs. This fluorine will also see 3 lone pairs, as will this fluorine. So we're using lines to represent our bonds and dots to represent the lone pairs. Make sure in the structures that you are drawing, your lines look like lines, your dots look like dots. If you erase, make sure you erase clearly. When you put these into your structure, make sure they are clearly present in your structure. You will not receive credit for dots or lines that are ambiguous. So make sure your answers are crystal clear. For this structure, we just gave 4 fluorines 6 electrons, and so that takes care of the remaining 24 electrons that we have, and at this point in our structure, we're out of electrons. So that as I continue through my rules, rule number 4 tells me to put any remaining electrons on my inner atom. I'm out of electrons, so that will not apply. Rule number 5 has me inspect the octet of the inner atom. And in this case, my carbon sees 8 electrons in the form of these 4 single bonds. So the carbon has its octet, the carbon is happy. As I double check my structure, I have all 32 electrons accounted for. And I have each atom in my structure seeing an octet. As I inspect my structure, carbon is my central atom, and as I look at the carbon, it sees an octet, and it has its octet in the form of 8 bonding electrons. It sees its octet in the form of 8 bonding electrons. I also have 4 fluorines in this structure, and each of my fluorines sees the same bonding pattern. Each fluorine has a single bond and 3 lone pairs to complete its octet. So in this structure, each of my fluorines is bonding to get to an octet, and it achieves that octet with 2 bonding electrons and a total of 6 non-bonding electrons, which come in the form of 3 lone pair. So if we look at a next set of examples, CH2O, this is the structure of formaldehyde. So in this structure, my atoms are carbon, hydrogen, and oxygen. And in this structure, I have one carbon that brings 4 valence electrons. I have 2 hydrogens that each bring 1 valence electron. And I have an oxygen that brings 6 valence electrons. That gives me a total of 12 electrons for this structure. That means that I have exactly 12 electrons to complete this structure. No more, no less. So as I start following my rules, I need to identify my central atom. Between carbon, hydrogen, and oxygen, the best choice is carbon. Hydrogen can't be a central atom, and oxygen is more electronegative than carbon. So that means I'm going to have a carbon in the middle, and I'm going to bond it to the oxygen and the 2 hydrogens. I've chosen to draw my structure like that. As long as you have the carbon in the middle, the other 3 atoms bonded to it, it doesn't matter whether you have the oxygen pointed to the left or to the right or anywhere in between. In drawing the structure like this, I used a total of 6 electrons, so that means I have 6 electrons left to complete my structure. As I continue following my rules, rule number 3 tells me to complete the octets for my outer atoms. My hydrogens will not take any additional electrons, so for my oxygen, it sees 2 electrons in this single bond. It will take 6 more electrons in order to complete its octet. So my structure looks like that. If I'm keeping track of my electrons, I just put 6 electrons into the structure, so I'm now out of electrons. Rule number 4 tells me to place any remaining electrons on my inner atom. That will not apply. Rule number 5 tells me that if the inner atom does not have a complete octet, I will need to make double or triple bonds. So this is where I will inspect the octet for my inner atom. My carbon in this case currently sees 2, 4, 6 electrons, so it does not yet have an octet. That means that my carbon currently needs 2 more electrons. Now, I can't just use my pen and put 2 more electrons on the carbon because I am out of electrons. So I have to use the electrons that are already in my structure to complete carbon's octet. So this is a case where I'm going to look to make a double or a triple bond by moving the electrons that are already in my structure around. What I'm going to do is I need an atom that has more electrons it can share with the carbon. My carbon is bonded to the hydrogen, which only sees the electron in this single bond. My carbon is bonded to this hydrogen, which also only sees the electrons in this single bond. Carbon is also bonded to this oxygen, which sees electrons in the single bond, but also in the 3 lone pairs. So as I make a double or a triple bond, I'm going to be looking for outer atoms that have lone pairs. Because what I'm going to do is I'm going to take these electrons and I'm going to share them with the carbon in order to make a double bond. So as I draw the result of that structure, I still have my carbon in the middle, I still have my 2 bonds to my hydrogen, none of that has changed. My carbon still has a bond to the oxygen, and these 2 lone pairs remain unchanged. What I have done is I've taken this lone pair and now it's going to reside between my carbon and my oxygen in the form of a double bond. So that this is the structure that now results from that original formation of the double bond, and this is the final structure, the final Lewis structure for formaldehyde. In this structure, my hydrogen sees a duet, this hydrogen sees a duet. This carbon sees 2, 4, 6, 8 electrons. It sees an octet. It is happy. All 8 of those electrons on the carbon are bonding electrons. My oxygen sees 4 non-bonding electrons in the form of 2 lone pairs and 4 bonding electrons in the form of that double bond. As I look at the next structure for HCN, as I first add up my number of electrons, I have a hydrogen, a carbon, and a nitrogen in this structure. Hydrogen brings to the structure 1 electron, Carbon brings 4 valence electrons, nitrogen brings 5 valence electrons, which gives me a total of 10 valence electrons to complete the structure. When it comes to my central atom, I know that hydrogen is never a central atom, so I'm looking at the electronegativity of the carbon versus the nitrogen. Carbon is less electronegative, making it my best candidate for the central atom. So as I connect my atoms, I'm going to put the carbon in the middle, and I'm going to bond the hydrogen and the nitrogen to the carbon. In doing this, I have used 4 electrons. I have 6 left. As I continue to follow my rules, rule number 3 tells me to complete the octets for my outer atoms. So I'm looking at my hydrogen and my nitrogen. Hydrogen will not take any additional electrons. It already has its 1 bond. My nitrogen has 2, 4, 6 electrons that it will need in order to complete its octet. And as I subtract those 6 from my total, I'm out of electrons. There are no electrons to place on my inner atom. And in Rule 5, because my inner atom does not have an octet, I'm going to need to look to make double or triple bonds. So as I do this, just as I did before, my carbon currently sees 4 electrons in the form of these 2 single bonds, so we know that it needs more. I'm looking to my outer atoms that have lone pairs that can share additional electrons with the carbon. Hydrogen has no lone pairs, it cannot help the carbon. My nitrogen has 3 lone pairs, so my nitrogen can possibly help the carbon. I want to do this systematically so that I make sure I end up with the correct structure in the end. I'm going to take my first lone pair from my nitrogen and share it with the carbon. That's going to give me a new structure that looks like this. In this structure, my hydrogen sees a duet, my nitrogen sees an octet, my carbon sees 6 electrons, 2, 4, 6, so my carbon is not yet happy. That means that I'm going to look again to my outer atoms for additional lone pairs that I can share, and as I look, I see that the nitrogen has another lone pair that I could share. So I'm going to take this lone pair and share it with the carbon, and that's going to give me a new structure. This structure has a carbon-nitrogen triple bond, and in this structure my hydrogen sees its duet, carbon sees an octet, 2, 4, 6, 8 electrons, nitrogen sees an octet, 2 in the form of this lone pair or these 2 non-bonding electrons, 6 here in this triple bond in the form of bonding electrons. So everybody's happy and I have all 10 electrons accounted for in this structure. This is the final Lewis structure for HCN.